Hello. Today we're going to be doing some studying ASMR, and yeah, let's get started. So today I'm going to be studying some discrete math and just getting ready for the quiz. Just got to prepare for it, so I'm going to have to study for a little bit. So let's go back into chapter 7. This is discrete math 2, so we're going to have to go back a little bit. I would like to re-review everything. Going back into chapter 1, which is all the way back, it starts with the introduction to graphs. Now, in these graphs, they are in a two-dimensional space, and there are two different types of graphs. One can be directed, and the other one can be undirected. So we're going to start off with undirected graphs. So undirected graphs is when there are vertices that do not have a specific direction. So the connection from point A to point B could point to either one of them. It doesn't necessarily mean that A is going to B or B is going to A. It means that it's undirected, hence the name. So this graph has, it's going to be finite simply because, it's not going to have infinite vertexes. Each different points are vertexes, and in between those vertexes, there are things called edges. So these edges are what connects the two vertices. So for instance, there's vertex A and vertex B. So what's the edge of vertex A and B? It's A comma B. So you can think of it as the amount of connections. And vertices are also known as nodes, but it's most commonly known as vertices. There's also something called parallel edges, where when two points have more than one way of connecting to each other, then there is essentially a parallel edge. And we also need to realize that there are implicit self loops. Implicit meaning that it's already it's known to have these traits. So for instance, we have a graph that's a triangle. There's points A, B, and C, and in point A it loops itself. It's not shown, but there is a implicit loop in the triangle. So if we go to a simple graph simply means that it is a graph that is that has no parallel edges or self loops. And even in a graph, there are a lot of like different terms. For instance, adjacent means that if there's an edge between the vertices. So an example of that is the edge DE are adjacent, but DB are not. Let me see. Oh, okay. So the definition of adjacent is like, it is very it's an interesting definition, because what it's trying to say is that if there's a connection between 2 points, then not only are they an edge, but they're also adjacent to each other. But if there is another connection, another 2 points that are not connected to each other, they don't have an edge, but they don't even have they don't have an edge, but they also don't have adjacency towards one another. So I guess you can think of it as similar. They go hand to hand with each other. Endpoint is the for endpoints, vertices are the endpoint if there are edges. It's interesting wording that I put out. So, okay, so endpoint are simply the vertex, the two different vertices. And the incident is what the vertex is, because the definition of an incident is that the vertices are connected by the edges. So, yeah. And then neighbors are also another definition, which simply implies that two vertices are neighbors because there's an edge that connects them. So, for instance, when we compared A and B, they're considered neighbors too because they are connected by edges. Now, there's also a degree of vertex. So the degree of vertex is the number of neighbor that a vertex has. So if we think about it, let's say there's a triangle A, B, and C, or points A, B, and C. Each point has 2 degrees because each point has 2 neighbors. Point A has connections with B and C. Point B has connections with A and C, and so forth, which, C has connections with A and B. So it makes sense that each and every one of them has a degree of 2. Now the total degree is adding all of the degrees. So the triangle that we just used, each of them had 2 degrees. So the total degree for a triangle is 6. Let me see if there's anything else we need to cover. This is chapter 7.1. Yes. Okay. There is a difference between a regular graph and a deregular graph. So in a regular graph, all the vertices have the same degree. But in a deregular graph, all the vertices have a degree D. So the graph below is a 3 regular. I see. So deregular graphs have a very specific there we go. So deregular graphs have very specific degrees. So each point is going to have the exact same degree. So for instance, a triangle is a 2 regular graph because each point, each vertex on the graph has a degree of 2. There's also another term called a subgraph. A subgraph is simply it's a improper version of another graph. So you can essentially assume that that subgraph could fit inside of the other graph. Now there's some questions here that let me just answer, why not? So there's a couple of questions. Question 1 states, is vertex C adjacent to vertex E? Now I know you can't see the screen, but if we're looking at this, from the way that I see it, C and E are not connected by anything. If we go back to our notes, it states that in order for them to be adjacent, they need to have an edge that is connecting to each other. So I am going to say no. What is the degree of vertex D? The degree of vertex D is the number of neighbor that it has. So D should have a degree of 3. Correct? Is the graph a regular graph? Is the graph a regular graph? So if we remember back to our notes, a regular graph states that it does not have a self-loop and it does not have a parallel edge. So from what I see, it is a regular graph. Oh, whoops. I mix the definition. A regular graph is different from a simple graph. A regular graph, let me go back to it. So a regular graph states that all the vertices have the same degree, but a deregular graph states that all the vertices have a degree d. So it is not a regular graph because there are different degrees for each vertex. Oopsies. So moving on. Question 4 states, is it correct to say that vertices D and E are incident? Going back to our notes, incident states that the two vertex must be connected to each other by an edge, I believe. And from the graph, yes, they are incident. Oh, okay. It says that it's not correct because an edge is incident to a vertex, but two vertices cannot be incident to each other. An edge is incident to a vertex, but two vertices cannot be incident to each other. I see. That makes sense. What is the total degree of the graph? Total degree of the graph. There are 5 points. Point A has a degree of 1. Point B has a degree of 3. Point C has a degree of 2. Point D has a degree of 3. And point E has a degree of 2. So if we're going to add everything up, it turns out to be 1 plus 3 plus 2 plus 3 plus 2, which turns out to be 6, 8, 10, 11. 11 degrees. What? Oh my god. It's 12. Because B is connected to A as well. So, instead of, it's 1 plus 4 plus 2 plus 3 plus 2. Okay, that makes sense. Is the following graph a subgraph of the graph above? Let's see, so BCE is V prime is equal to BCE, E prime is equal to BCE, comma B. I'd say that they're a subgraph. It looks to be the same. Yeah. They're all vertices, so it makes sense. Now there's another theorem in 7.1 that talks about the number of edges and the total degree. So this specifically refers to an undirected graph, stating that let G is equal to the vertex comma the edges. Let graph is equal to the vertex comma edges be an undirected graph. Then twice the number of edges is equal to the total degree. So 2 times the number of edges equals the degrees in an undirected graph. What is the sum of degrees in the vertices in the graph depicted? So if we're gonna be looking at the graph, it looks as if, it looks like there are 5 different points. The first point is connected to 2 edges, or yeah, 2 edges, so that's 2 degrees. Second is connected to 1, 2, 3, 4. The third is connected to 2, and then the fourth is connected to 4, and then the last one is connected to 2 as well. Which means that the total degree is 8, 12, 16. Whoops, 14. 14 should be the correct. Yep. And also, it also makes sense. Like the theorem makes sense because if you think about it, you can also count the total number of edges, right? The number of edges there are is 7. So 1, 2, 3, 4, 5, 6, 7. Multiply that by 2, and you get the total degree. Which of the following statements describes the inductive step in a proof that proves a theorem about a graph by induction on the number of vertices? Assume that a theorem holds for a graph and then show that the theorem holds after a vertex is removed from the graph. It describes start with a graph and remove a vertex. Assume that the theorem holds with a graph and with the vertex removed, and prove that the theorem holds with the graph when the vertex is put back in. I don't really understand the question. Which of the following statements describe the inductive step in a proof that proves a theorem about a graph by induction on the number of vertices? I don't know, that's a bit of an interesting question. How would I go about solving this? There's 2 possible answers. I just don't know which to pick. Like in an exam, I'm not gonna just say, oh, it's gonna be this or that. I need to have a reasonable explanation as to why I got this. That way I can actually, be confident that I selected the correct answer. Start with the graph and remove a vertex. Assume that the theorem holds with the graph with the vertex removed, and prove that the theorem holds with the graph when the vertex is put back. Let me see what the term induction actually means. The process of or action of bringing about or giving rise to something. It's a pretty popular topic in cooking, so that's interesting. Let's see. Assume that the theorem holds with the graph. I'm gonna assume this. Yeah, okay, so that's correct. Okay, interesting. I see. Okay, so let's go to 7.2. We'll finish it off with 7.2, which actually is not too difficult. So 7.2 states that there are 2 drawings of an undirected graph. They look different. However, they're only different because they're drawn differently. But they're the same graph because they have the same vertex and edge sets as shown below. So they have the vertices A, B, C, D, E, and they have the same number of connections, the same equivalent connections to each vertex. There's 2 questions. It's going to indicate whether the graphs shown are the same graph. Let's see if they're the same. A is connected to E and B. Okay. Yeah, I think they're the same. Yeah, they're slightly different, but if you orient the shapes correctly, they have the same number of vertices and they have the same number of connections to each of them. Okay, so C is connecting to A. Okay, they're different because I can already see that they shifted. The second question, they shifted the vertex by 1, so it's like in different positions now, and the number of connections have changed. So in 7.2 it talks about adjacency list representations for graphs. So in the adjacency list representation of a graph, each vertex has a list of all its neighbors. Note that since the graph is undirected, if a vertex A is in B's list of neighbors, then B must also be in A's list of neighbors. Makes sense, makes sense. The animation below shows the adjacency list representation for a small example. Okay. So a neighbor's list for vertex B. Okay. That makes sense, that makes sense. So A, B, and C are connected. So A has 2 different connections, which is B and C. And I'm assuming they're going to do the rest. B has 3 connections. Yeah, that makes sense. C has 3 different neighbors. D has 2 different neighbors. And E has 2 different neighbors. And we're determining, so from the question is B adjacent to C? Well, using this adjacency list, we see that we know that C is inside, so C is a neighbor of B and B is a neighbor of C, which states that they are adjacent. It's an interesting, see, some of these things are like a little bit like redundant, but I guess like if you want to do it in like a mathematical way, it makes sense. Like you can do it in such a way. Now comes the more interesting part, which is the matrix. So the matrix is going to be, it's a graph. It's going to be like a, depending on the how big the vertex is. For instance, this one has a vertex of 5. There are 5 different vertices. So in a matrix, you need to make a square. You need to put 1, 2, 3, 4, 5 in the rows, but you also need to put 1, 2, 3, 4, 5 in the columns. So let's do that really quickly. Okay, and then 1, 2, 3, 4, 5. So looking at this, we know that 1 to 1, we put zeros wherever there is no connections, whether or not each edge is present. Okay, so if there's an edge, then it's going to be a 1. If there's no edge, then it's going to be 0. So we can put a diagonal 0 from each and every one of them because there is no edge between 1 and 1. There is no edge between 2 and 2, and so forth. Okay, so that works. Is there an edge between 1 and 2? Let's see. Yes, there is. Is there an edge between 1 and 3? Yes, there is. There's no between 4 and 5. Is there an edge between 2 and 1? Yes, there is. Is there an edge between 2 and 3? Yes. What about 2 and 4? No. What about 2 and 5? Yes, there is one. So we put a 1 there. What about 3 and 1? Yes, there is. What about 3 and 2? Yes, there is. What about 3 and 3? Nope. 3 and 4? Yes, there is one connection. And finally, 3 and 5. No, there's no connection. Doing 4 and 5, let's go. So 4 to 4. 4 to 1, there is no connection. 4 to 2, nope. 4 to 3, yes. 4 to 4, nope. 4 to 5, yes. So for 5, there's no connection for 1. There is a connection for 2. There is no connection for 3, but there is a connection for 4. Perfect. And just like that, we have the matrix. Now there's a couple of participation questions. Let's answer them really quickly. So the diagram shows 2 graphs. Question 1 states, which of the 2 graphs above corresponds to the following matrix representation? The rows and columns of the matrix are numbered 1 through 5. So if we're gonna look, 1, 2, and 3. Okay, so immediately I can see that it's graph H. Yeah, because the first graph is connected to 4, but the second graph is not connected to 4. But in the matrix, it says that the graph is not connected. The first vertex is not connected to 4. Therefore, it is graph H, not G. The second question states, which of the 2 graphs above corresponds to a following adjacency list representation? So if we're looking at this, 1 is 2, 3, 5, 2, 3, 2 is 1. Okay, it should be graph H again. Yeah, it's not too difficult. And our last question, which is going to end off the ASMR. So, fill in the missing entries to complete the matrix representation. 1 is connected to 3. Is that true? Yes, that is. So we put 1. What? Oh, it wants me to put the whole thing. Okay, that makes sense. So 1 is going to be connected to 3, correct? What about for B? It says, is 2 connected to 1? No, it's not. C is asking if 3 is connected to 1. Yes. And is 4 connected to 1? Yes. Perfect. That's correct. There we go. I believe that was a bit of a shorter ASMR, but I do hope that you enjoyed it. And yeah, thank you very much, and I will see you tomorrow or whenever I record.